Okay, so today's session probably won't be, you know, very long, um, but I'll try to show you some like the basic principle that Quantum Espresso uses to compute the you know energy levels, and and I'll probably try to show you another thing I've been doing, running. You know, I've been trying to calculate the density of states and band structure for a material. Um, and when you run quantum espresso, you first need to do some kind of convergence test. Like if your computations are approaching toward a stable and stable value or something. And to do that, you need to perform some tests on different grid side, different energy cutoff, and like a lot of things. And for self-consistent field calculations, it's kind of easy because you just have one number, the total energy. And if the total energy is constant, even if you change the grid size or the cutoff energy, then you are in the stable or in the equilibrium. Like increasing the grid size or the energy cutoff may not affect the calculations that much. But for density of states and band structure, it's not always that straightforward. You don't have a single quantity. You kind of need to plot and see the density of states, the spikes and peaks of the bands as well, and see if if it changes, if you change one or more parameters, and then decide kind of which parameters you want. These tests are important because when you publish your result, for example, you want to be confident that this is correct given the approximations. You always need to mention the approximations that, based on these approximations, these are the uh, bands and density of states. And okay, let's start. And I'm thinking Alvi said he's having some issues running codes, but he won't be able to join today probably. So what I'll do today, I'm just gonna show the basic Kohn-Sham algorithm and the Python code to run this simple like calculations on a system of two atoms per site lattice. And tomorrow, we're gonna just have a kind of question answer session. If Alvi is kind of free tomorrow at that time, and you guys are free, probably it will be um, 7 p.m. Bangladesh time. Uh, I don't know. It could be half an hour or maximum 1 hour, just to kind of solve the problem so that you guys don't have to wait for another week to get the problem solved and actually run the computations, because you kind of need to present, so you need to um, get going, and these technical issues shouldn't be the problems to hold you back. Okay, so let's start today's session. let me uh, let me share let me join from my iPad and share my screen. What is the Zoom?
Recording in progress.
um, okay, share screen, start a broadcast. Okay, let me. Okay, so you can see my screen, right?
Yes, we can.
Okay, okay, good. So in DFT or quantum espresso, they use a kind of I mean, at least the simplified version is the Kohn-Sham algorithm. It's basically, the idea is really simple. You write down the Schrodinger equation with an effective potential uh, and uh, this is simply the Schrodinger equation. It's like H psi equals E psi. And H is the operator, E is the eigenvalue, psi is the eigenvector, right? আমরা লিনিয়ার অ্যালজেব্রা যখন ডিসকাস করলাম তখন দেখেছি যে what are the eigenvalues and eigenvector? Especially you have an operator or a matrix and there are certain vectors. If you do a matrix product, essentially it's just multiplying the vector with a scalar. Meaning a matrix প্রোডাক্টে ভেক্টরের লেংথ জাস্ট চেঞ্জ হয়, ডিরেকশন চেঞ্জ হয় না. Those are like special vectors. Okay, and in this Hamiltonian, this is the first term is the kinetic term, and second term is potential term, potential energy. Now, kinetic term is just একটা single term আছে, right? But for the potential energy term, it's called effective potential because, you know, kinetic term is simple. কিন্তু potential term মধ্যে it depends on the configuration of your system, meaning different material, different atom, and if you consider relativistic or not, spin orbit coupling or not, that will change the form of the effective potential. So that's why it's called effective potential. And so one approximation is this: the effective potential is the um, external potential or pseudo potential plus the Coulomb interaction between electrons, or the Hartree potential. Hartree potential or Coulomb interaction between electrons plus another term, which is the exchange interaction, is basically anything that cannot be captured by Hartree potential is for many, you have electron cloud, right? Instead of interaction between electrons, you want to consider what happens due to the electron cloud, kind of quantum many-body interaction potential. And this is there are different approximations. One approximation is LDA, or local density approximation. Another density, I think, generalized gradient approximation. Approximation. So there are different approximations. Essentially, is it's exchange correlation or quantum many-body. there are expressions in each approximation, so somehow you can compute it. So the pseudo potential is basically, for a material or for an atom, what is it's like the Coulomb potential, but it's kind of for different atom is different. And the pseudo potential that we provide in quantum espresso, that's basically the first term, this term. Okay. Okay. So the Hamiltonian is then my kinetic term plus this potential term, right? And then it's kind of straightforward because you see the equation is this: H psi equals E psi. So if you have the Hamiltonian, you can find the eigenvalues and eigenvector. Eigenvalues will give you the energy, and eigenvectors will give you the wave function psi. Now, the question is, how do we compute pseudopotential, Hartree potential, and exchange interaction? How do you compute this, or how do we find these? To find the pseudopotential, okay, V is basically let me just draw the diagram. It's basically some kind of Gaussian potential at each atomic site. Gaussian potential at okay. So that's kind of simple. If you want to generate, given the parameters for Gaussian distribution, you can always generate this potential at each atomic site. You can also use the external pseudopotential provided in those websites. Now then, how do you get the Hartree potential? The Hartree potential obeys the Poisson's equation, which is del square V h of x equals minus 4 pi n of x. Now this n of x is the electron, there's the charge density, which is basically psi squared dx. To get the Hartree potential, you just solve this equation, because this is what we need, VH. Solving this equation is kind of straightforward, because what we do a Fourier transform, and assuming V of h of x is equal to some kind of e to the power ikx form times some other function, for example, function of k. So when you do the Fourier transformation, you there is del squared, right? Wait a minute. Yeah, because of del squared in Fourier transformation, because of the del squared, you get okay. So if you have e to the power minus ikx, you do d dx, what do you get? You get minus ik e to the power ikx. And if you do it twice, you get minus ik whole squared, right? And this is basically minus k squared e to the power minus ikx, right? That means this del squared, or second derivative, gives you a minus k squared. So here we get minus k squared VH as a function of k in momentum space equals minus 4 pi n of k. This is a function of x, it also becomes a function of k. Sometimes we write it as rho of k, just a different symbol. Then v of h of k is just 4 pi rho of k over k squared. So once you have an expression for v of k, you do an inverse Fourier transform and get v of x. Um, there's like up to a plus minus sign and normalization constant. Okay, so that's the basic idea, like solving it using Fourier transformation. Okay, and then for the exchange interaction, there are expressions like for local density approximation, the expression is what is the expression? So V exchange interaction, the expression is minus 3 n of x over pi to the power 1/3. I don't have a good explanation for this expression, but expression is there. And if you notice one thing, we have n of x here, and here as well we have n of x. That means to compute these, VH or exchange interaction, we need this n of x, which is, a psi square, meaning it's like a. So the way this quantum algorithm works, we approximate this n of x. Let's say this is the first n0 of x, and solve the Schrodinger equation. H psi equals E psi, and here H equals kinetic energy plus pseudo potential plus V exchange, the Hartree potential plus V exchange, and we have n of x here and here, which is our n0 of x for now. And next step is to get the eigenvalues and wave function, compute n1, n of x, which is psi squared, right? And then the new charge density, there's some kind of, so using some initial approximation, we solve the system, find new charge density, n of x, and then instead of taking the new charge density, we take some part of it. So n0 of x plus, let's say, okay, let's say 0.2 n of x plus 0.8 n0 of x. Meaning we're taking 80% of the old charge density and 20% of the new one. Then we get new charge density. Then we iterate this whole thing again. And we keep doing this until we see some kind of convergence for this charge density n of x. When we see that, so we get n from n0 of x, we do some computation, find n1 of x, and do some computation again, find n2 of x. We keep doing this. When we see that in k of x minus n k minus 1 of x, I mean charge density between consecutive steps, the difference is less than some, I don't know, some tolerance, let's say 10 to the minus 6, then we say, okay, these are converging toward a kind of constant charge densities. That means we are approaching the correct solution. Then we stop the computation. Does it somewhat make sense?
Yes, it does.
Okay, that's the basic concept of how this works. Now, if you want to go into details, like, you can spend very long time figuring out this exchange interaction. Now, which one is better for which system? You can also spend time with the pseudopotential, because you see there are a lot of different pseudopotentials, right? Like if you want to include the spin orbit coupling, there are different pseudopotentials. If you want to include partial relativistic or fully relativistic, you have different pseudopotential. So it's like a lot of space to explore to find the effective potential, right? And for the Hartree as well, but Hartree is kind of done more or less internally, like pseudopotential file you provide, but other things are internally done based on, I think, your inputs. You can also kind of provide some parameters to tell Quantum Espresso to use a particular approximation over the other, but this is the main idea. Now let me show you code. How do you stop sharing? Stop share. Okay. Let me show you my code that I tried. Okay, can you see my screen? Oh, probably.
Yes, it is visible.
Okay. So I tried,
Could
the,
you resume recording?
it's not, I think it is recording, but
Okay, my
yeah, it's
mistake. Yes.
recording. Yeah. Okay, so here I have the simple code for Kohn-Sham algorithm. Let me just briefly explain what's happening here. So first, for any kind of numerical simulation, you need some kind of, you need to set up a grid, right? So the grid is here n equals 1,000 grid point, and length of the system is 10, unitless. Everything is unitless, meaning our variable x runs from minus L over 2 to plus L over 2, and we are taking 1,000 points in that line. So dx, the step size is just, difference between 2x. Okay. Now the pseudopotential is simply the Gaussian potential, as you can see here. So whenever you see exp minus x squared, that's Gaussian. And you can tune the width and height using the sigma and strength. And we have Gaussian potentials at the center of each atom. So we have these 1,000 points. At each point, I think we have 2 atoms. Okay. So it's like to the left and to the right of those each side. This is just some kind of approximation, like basic code to show you how it works. Okay. And then we have an approximation of the initial electron density. Okay. Then we have the kinetic operator. So you see the kinetic, I think I have the expression, yeah. For the kinetic energy, we have minus h bar square over twice m del squared. So when you have del squared, if you want to express it in terms of matrices, it's done using this, like it's using finite difference operator. So what you can do to see how it works, let me just copy this, and yeah, I have it here. So let me run the test. Python test. So it's okay. So I have a matrix where how do I write this? So the 0, 0 element is 2. So these are all diagonals, right? 0, 0, 1, 1, 2, 2, 3, 3. All diagonals are 2. And this is 0, 1, I mean 1, 0, 2, 1, 3, 2. Off diagonal uh, of the upper upper triangle, and this is the off diagonal of the lower triangle. They are -1. So here is saying that um, diagonal 2, off diagonal -1, and I don't remember what this is. But we can test. But this is the idea of when you have second derivative, this is the way you express it in a matrix. I think I have it in my notes somewhere. Let me just try to find it. Uh, just a minute. 5, 4.
Well, in the calculation, something seems a bit off.
Where?
It's a 4 by 4 matrix essentially, and that's why we got four diagonal terms, all of which are 2. But in a 4 by 4 matrix, we should get 6 off diagonal terms on upper side and on lower side, 6 on each side. But we are
Oh,
getting
yes,
3.
good point. Other terms are 0.
Okay, okay.
All the remaining terms are 0. But yeah, that's a good point. I can. Okay, how about this? After the class, I'm just going to post a document showing how you express, um, you know, uh, I think I have done it somewhere, but it seems I cannot find it right now. But I'm just gonna post it. It's really simple. Like you take the first derivative and second derivative in express in terms of matrix. It's kind of really straightforward. Okay, but let's just keep moving for now. So you have your kinetic operator, and then for the Hartree potential, remember we solve using a Fourier transformation. So yeah, this is the equation. So this is the Poisson's equation, and this solution for Hartree is V of k equals 4 pi rho over k squared. So here I have V of k equals 4 pi rho up to a sign. I think I missed the sign somewhere, over k squared. Here, instead of k, we have g. And this 10 to the minus 10 is written there so that we avoid dividing by 0. Okay. And we also set this first element to 1 because after when you do, how do you get the k? We take Fourier transform of those grid points and we get the k and some factors. And when you have v of k, we take inverse Fourier transform IFFT. So here it says f of t, FFT because it's fast Fourier transform. It's like a numerical method to get the Fourier transform done in a finite system. And we take the real component, we get the Hartree potential. And for the exchange interaction, for local density approximation, the expression I found is this. 3 times n over pi raised to the power 1/3. So we have three different types of potential. What is this? External, which is the pseudopotential, Hartree potential, and exchange interaction. When you have all these, we solve the Kohn-Sham method. So we set up a loop. We find the Hartree potential given the charge density. We find the exchange potential given the charge density. We find the effective potential, Hamiltonian, and find the eigenvalues and eigenvectors. Using the eigenvector, we find the new charge density, and then we check for the convergence, the tolerance. Remember, if the tolerance is less than a number, the difference, then we stop. So this line, last line here. In our case, the tolerance was 10 to the minus 6. Here we have TOL, which is 10 to the minus 4. And if it's not, then we take 20% of the new charge density, 80% of the old charge density to define new charge density for next iteration. And we do it all over again. We keep doing this until a convergence is reached, or we do like maximum number of iteration. And then we have the energies, the wave function or the eigenvectors, that new charge density at the effective potential. Then here it's plotted like everything we have found so far. Let me just run this code too. And it's doing the computation. Okay. I guess it's gonna take I don't know, a few seconds. Maybe I should change some. Okay, it's done. So here I have the blue one is the pseudopotential, and the orange one is the effective potential. And then we have the orbitals, quantum orbital. Like this is one state with energy minus 2.7, and we also have the electron density, the final electron density, and the Hartree and exchange potential after doing all the computation. This just shows like how it kind of works. So if we plot all these before doing the calculations and after, you'll see the difference. Let's try that. Do we have okay. I want to do it before and after the computation. So let me copy this, go here. But before, I don't have this VXD. Let me just take number of electrons equals 2. Equals 2. Okay, so let's run it again. You see, it's different, right? The pseudopotential and effective potential, and Kohn-Sham orbital is also different. Charge density will have like two at two side, -2 and +2. Then it converges toward something. This just shows like the basic steps. I don't think this is fully accurate, but it probably just give you the idea. Now you want to if you want to perform the computation, like write your own code, it's going to take some tuning, like fine tuning. Okay. Any questions?
No.
Okay. Now, excuse me. Let me try to show you another. Okay, so let me. What is that? Oh, yeah. So as a last kind of say topic for today, let me show you how I've been doing this parameter optimization or relaxation computation and convergence tests. So I have this TCL script written, and here first I'm doing the variable cell relaxation computation. Then these commands is kind of complex, right? So what it does, so the way this script works, first I have an initial STF computation input file, which is this one, right? Here I have like almost everything defined, atomic position, K points, and everything. So I'm loading that file using PWTK so that I don't have to write everything here again. Then setting some parameters for the relaxation computation. Then I'm running the relaxation here, which is commented right now. When I'm like done running this relaxation computation, I have some output file, which is okay, SI relax out. This is the file, and here I will have optimized atomic position. So cell parameters. Okay, so let's see is if I search cell parameters, it appears in 10 different places. ওকে, কারণ হচ্ছে এটা মানে 10টা ইটারেশন হয়েছে। প্রথম ইটারেশন থেকে দ্বিতীয় ইটারেশনে সেল প্যারামিটারগুলো একটু চেঞ্জ হয়েছে। So if I go to the last iteration, I get the final cell parameters and atomic positions. Now, for next steps of the computation, you can copy this manually to your STF file and run the code, or to an STF file, or you can run these commands that will copy the last cell parameters and atomic position in that output file, which is kind of convenient, right? So cell parameter is copied to this variable, atomic position is copied to this variable, and then I can run another STF computation using the optimized cell parameter and atomic position. Then I just print the total energy, and that's it. Okay, so step গুলি হচ্ছে, first you do VC relax or relaxation computation. There are two types. Uh, 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 okay, so for relaxation, we have relax or VC relax. Which one you run, it depends on like your kind of need. VC relax kind of more, you vary the cell parameter and atomic position both in your computation. But in relax, you just vary the excuse me, atomic position, not the cell parameter. Let me cross this. After running the VC relax, you run using this optimized cell parameter and atomic position, You can run a self-consistent computation, find the energy, and then we scan for a cutoff energy optimization, this code. So which is, you see this E cutoff for the wave function. If you go to the SCF file, you'll see this E cutoff wave function. So there's like a, what the energy should be in the Rydberg unit for the wave function. And, here I try to run for 20, 30, 40, 50, up to 100. And each time I generated this output file. And then I have those, for all these cutoff energies, I have extracted the cutoff energy for different computation in this file. So I have this first column is the cutoff energy, and second column is the total energy. And when you plot that, we see that the total energy decreases as you increase the cutoff energy and it reaches a stable kind of value after 40 or 50, right? So the idea is approaching a constant value. So that means in your computation, if you use 50 for the cutoff energy versus using 90, in terms of total energies, that's going to give you same total energy. And that was done in this mesh 12, 12, 24. But if you use 90, that's going to take more time. But if you use 50, that's going to take less time because lower cutoff energy means you have fewer plane waves in your expansion. So it's like faster computation. But this graph shows that our calculations approaching a constant total energy. That means we are more or less in the optimized region in our computation. Okay, does it make sense somewhat?
Yes, sir.
Okay, so yeah, when you do computation for a material, you need to run these initial tests, and that can take some time. This PWTK allows you to kind of do it simply, right? Like this, you have if you load the SCF file and do some VCRelax, but if you want to skip VCRelax, you can delete all these, right? So you load your SCF file and then let me delete all this. You load your SCF file and you run the computation. So evar is this. Just change system name list, ecutoff, and erow. Run the computation. That's it. And in next step, we can extract the total energy from the output file, right? Because if this is the input file, the output file will be this name dot out. And we can write to a file and then plot the graph, which is, it saves a lot of kind of trouble when you want to do this parameter optimization. That's why I introduced this PWTK. Okay, after this energy optimization or total energy optimization using the cutoff energy, you also want to optimize for the mesh size that you use. So K-mesh, it can be 336, 6612 in my case, and then I run this computation. This line is commented right now, and find the total energy, write it to a file, this file. So I have this K point, 8, 8, 16, 10, 10, 20, 12, 12, 24. Okay, this is the final K point graph, 336 to 12, 12, 24. And if I plot that, you see the total energy is approaching a constant, right? It increased, then it's like kind of approaching a constant. That means if we use 8, 8, 16, this point, or 10, 10, 20, this is just nx along x-axis, we're going to get the same total energy for E cutoff equals 50. So we have optimized for K-mesh and the cutoff energy for the wave function. Does this somewhat make sense? Like optimization steps?
Yes, it does.
Okay. Then next step is to do the NSCF computation, and we can also optimize there. But NSCF is little kind of involved because for SCF computation, we have a quantity, the total energy that we can, try to minimize or maximize for different parameters. But for NSCF, we don't have a single quantity. We have to plot the density of states or the band structure and look for some kind of sharp changes and see if we change the parameters, how those how those sharp changes get affected for different parameters. So I've written this relax 2, relax 3. Let me just show you relax 3. So, I have this cutoff energy 50, and here I have run this computation for grid nx equals 18, 20, 22, up to 28. If nx is this, then nz would be 2 times nx, and my grid points are nx, nx, and z, meaning 18, 18, 36. And last one was 28, 28, 28 times 2. Because the density of state can be different, or the Fermi energy. I was able to set this loop. So for each of these nx, I ran the NSCF computation, the bands computation, the density of states, and it generated me, density of states for nx equals 10, 12, 14, 16, up to 28. So running all these one by one is kind of time consuming, right? But if you can set up a loop like this in TCL or PWTK, it's kind of convenient, right? You can do it by hand manually, but এখানে কয়টা করতে হয়েছে 10 থেকে 28, it's like 1 2 3 4 5 6 7 8 9 10, 9-10টা করতে হয়েছে, আরো বেশি করতে হতে পারে for complex systems, and there like আর অন্যান্য ভ্যারিয়েবল থাকতে পারে যেটা তুমি অপটিমাইজ করতে চাও. So that's why TCL is kind of interesting. So now যেটা আমি এখন kind of দেখাতে পারি, I can try to plot the density of states. So first column is the energy, second column is the DOS. Let me just try to plot all of these on top of each other. Okay, so I'm just going to write a Python code, and probably that's okay. So import numpy as np. Like I just increase the font size a little bit. Okay. For nx in 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. File name equals tdos_.dat format nx. So if you don't understand Python command, just tell me, okay? So I'm going to print the file name just to be sure. Then I'm going to read the file, and the data will be there. And here, let me just see. Skip the first row, but in first row you have the Fermi energy, right? Which is important. But we have almost same, but initially it was different. So we'll need to use the Fermi energy for our plot. So let me plot plot the data, first column, second column, label equals NX, format NX. There are different ways to write this, but uh, so I'm running this computation in the server, so that's why I need to save the file. I cannot just view it. Okay, so tdos.png. Yeah, so x limit should be -1 to 1. We want to see what happens near the Fermi level, and x equals this, y equals this, x, y. So x minus E Fermi. Fermi energy is important, so otherwise it will not be aligned. Open for read. Fine. Okay, so I'm gonna let's set the Fermi energy to 0 for now, just to see how it looks. Quantum espresso, NB3 S4, TCL2, Python TDOS plot.py. Let's see how it looks. Okay, so I have different Fermi energy a little bit, but see the y-axis is way off. So let me turn off the limit for now. So there's a peak at around -20. That's why y-axis was off. So, but we need to see what's happening near the 0. Okay. So what we're going to do, we're going to set the limit for x and y. For y, it will be 0 to 5, let's say. And I think, I don't know, maybe I missed it. 10. Maybe I'm missing it. Or -5 to 5. Okay, now we have something. So at 0, we don't have anything for some reason. But we have something at -2. And can you tell me why this is happening? At 0, we should have something because this material is conducting. So the way it looks here, let me remove the limits. So if you have read this, that density of states paper, you'll know this. The way it looks here, that near 0, we don't have any density. And that means that this material is not conducting.
This band gap actually.
Band gap, yes, exactly. But this material we know is conducting. It's actually Nb3S4 is conducting. Resistivity is not too high. So what's happening? The reason is we haven't subtracted off or shifted the energy levels accounting for the Fermi energy. That is the problem. If we shift, then we'll see this 10 you see, I think that's gonna be over there near zero. So the way we're gonna do, so that's why I was printing the Fermi energy 11, right? So I need to extract it. The I think split will do it probably. So that is the number second last. So -2. And if Fermi equals float, hopefully that will work. Let's see. It should work. I think it did, but yeah, it did. See, 0 is here now. And we can use this plot. So there, the height is 20. So I can do 20 minus 1 to 1. Right? Okay. So here we can see that for almost all the computation, the Fermi energies are kind of lining up. I don't see any significant difference, right? And near zero, we have some density. So this is how you kind of check. For this case, they're lining up kind of quite well, but I think I need to explore more to see also, when you compute the Fermi, the density of states, you have to set this minimum, maximum, and delta E and D Gauss. If you change these, that can also change the distribution of the density of states. So, if consider an example, if I had for nx equals 10, I had different shape, but then, for example, that point, let's say it was there, and as I increased nx, it was approaching this point for higher nx. That would mean that we need to use that higher nx to get the converged computation. Does it make sense somewhat?
Yes, sir.
That's kind of the thing we need to do for density of states. Also for the bands, I haven't plotted the bands. Probably gonna do it after, like this. This is my project, so um, I'm gonna do it at my own in my own time. But yeah, more or less, this is how you do it. You change one parameter, do these convergence tests, and so that you have confidence in your result. And oh, yeah, this is more or less it. Anyone, do you guys have any questions?
Not right now, sir.
Okay. All right. So tomorrow, I'm gonna ask this question in the group if anyone wants to discuss any kind of technical issues. Tomorrow, probably, I don't know when, Bangladesh time 7 or 8 a.m. Sorry, p.m. for like half an hour. We're gonna have a session just for technical issues, so that you guys aren't stuck solving those technical problems. And yeah, this is it for today. And another goal was to show you how to compute the topological invariance from the Hamiltonian. I have discussed the Hamiltonian, like how to get the Hamiltonian, but not how to use it to do some computations, like calculating those invariants. Um, I don't know if we'll have time, but if we do have time, we're gonna do that. Like uh, I made some progress there, but it's kind of involved. We'll see if we can, manage time. We'll do that. Okay, so I guess this is it for today. So yeah, see you guys next week, and start preparing for your presentation. It can be anything, but for like 20 minutes to half an hour presentation. Try to try your own example, like the materials you're interested in. It could be a topological material, it could be insulator, or any material that you feel interested, or some materials that you have worked on previously. You can use this optimization, how to use TCL, PWTK. Okay. Um, yeah, try to prepare and let me know when you kind of select a topic, because I want to make an announcement before you present, so that most students can be there for your presentation. And yeah, this is it. If you don't have any questions, that's it. Take care. See you next week.
Sir, like if you have a bit of time, I have some unrelated question actually.
Okay.
Okay.
Do you
You
want me
can
to
stop
turn off
recording.
the recording, or?
You can turn off. I don't think it's necessary.
Okay. Okay.